Hello and welcome to the channel. Yet another problem from American Region Mathematics League competition year 2022, and the last in this channel. In fact, there are other assignments in the competition, but firstly, I don't find them exciting enough. Secondly, I believe 3 items is just right for anything. So we need to find the least number whose sum of digits in both usual decimal system and octal system, which is the system base 8, is 10. Please be aware that in both cases the sum is taken in the corresponding system. Here we got an example for number 23 corresponding to 27 in octal system, and when two octal digits 2 and 7 are added up, the result is not 9 as someone may expect, but 11. As 11 is the octal representation of number 9. So please pause the video and try to solve on your own. Number 10 in octal system is equal to number 8 in decimal. So we are effectively looking for a number whose sum of digits is 10 in decimal system and 8 in octal system. Whenever sum of digits is concerned, the first thing coming into mind is divisibility by 9. It can be formulated in the following way. A number divided by 9 gives the same remainder as its sum of digits divided by 9. This works for decimal system, but not for octal system. In fact, octal system has something similar, which will be discussed later. But one thing is certain. Since the sum of decimal digits must be 10, the number we are looking for divided by 9 must have the same remainder as number 10 divided by 9, which is 1. In other words, subtracting 1 from the number must give a multiple of 9. So let's write that as a reminder. And this is what we are going to do. We are looking for a number whose octal representation has the sum of digits equal to 8, while subtracting 1 from this number gives a multiple of 9. Of course, this doesn't guarantee that the sum of decimal digits is 10, because it can be, for example, 19, which also gives remainder 1 divided by 9. This means that trials and errors cannot be completely avoided. However, we will try to do our best to minimize that. Quite obviously, a single-digit octal number is not what we are looking for, as the sum of its digits is the digit itself, while an octal digit is certainly less than 8. So we start with a 2-digit octal number named P having digits A and B. The line above indicates this is not A times B, but a number composed of digits A and B, while subscript 8 shows that this is an octal number, a number written in base 8. The sum of digits A plus B must be equal to 8. A is a leading digit, so it must be at least 1. At the same time, as an octal digit, A must not exceed 7. Digit B can be 0, but it also doesn't exceed 7. The value of P is 8 times A plus B, where we can substitute 8 minus A for B. Then we reduce common terms and find that P equals 7A plus 8. Hence, P minus 1 equals 7A plus 7, where we can factor out 7 and get 7 times A plus 1. But P minus 1 must be a multiple of 9, while 7 and 9 are coprime. This means that A plus 1 must be a multiple of 9. However, since A is no less than 1 and no more than 7, A plus 1 must be in the closed interval from 2 to 8. while there is no multiple of 9 in this interval. So bad luck with a 2-digit octal number, and we need to try an octal number consisting of 3 digits, A, B, and C. Now A plus B plus C equals 8. A is no less than 1 and no more than 7, while B and C are non-negative and don't exceed 7. 8 squared is 64, so P equals 64A plus 8B plus C, and we replace C with 8 minus A minus B. Again we reduce common terms and get the expression for P minus 1, where we can again factor out 7. Again we want P minus 1 to be a multiple of 9, but since 63 is divisible by 9, the whole first term is divisible by 9. Therefore, the second term must be divisible by 9, which means that B plus 1 must be a multiple of 9. Digit B can be 0, so B plus 1 must belong to the closed interval from 1 to 8. However, neither this interval has a multiple of 9. Bad luck again. So there is nothing better than considering a 4-digit octal number A, B, C, D. Now A plus B plus C plus D equals 8. A is no less than 1 and no greater than 7. B, C, and D are non-negative and don't exceed 7. 8 cubed is 2 to the power of 9 or 512. So P equals 512A plus 64B plus 8C plus D. Next we substitute 8 minus A minus B minus C for D and reduce common terms. Factor 63 is divisible by 9, but factor 511 isn't, because its sum of digits equals 7. Again 7. Don't you think it appears too often? Anyway, 511 minus 7 is 504, and this number is divisible by 9. So we represent 511a as 504a plus 7a. Again, we get the expression for P minus 1, where we can again factor out 7. P minus 1 must be divisible by 9. First two coefficients in the expression are divisible by 9. Therefore, the first two terms are certainly divisible by 9. Consequently, the last term must be divisible by 9, and A plus C plus 1 must be a multiple of 9. This is much better than in case of 2 or 3 digit numbers. Indeed, adding up the inequalities for A and C and increasing the obtained inequality by 1, we get A plus C plus 1 is no less than 2 and not greater than 15. The closed interval from 2 to 15 contains a multiple of 9, but only one such number. This is number 9, of course. Therefore, A plus C plus 1 must be equal to 9, in which case the sum of A and C is 8. But 8 is the sum of all digits, including digits B and D. Therefore, digits B and D can be only 0. This means that octal representation of number P is A0, C0, where A plus C equals 8. Also, in the expression for P minus 1, the second term is 0, and since A plus C plus 1 equals 9, the third term is just 7 times 9, or 63. So P minus 1 is 504A plus 63, and P equals 504A plus 64. Now we can wipe out some lines of the page. and copy some of the obtained equations to the top. Now we have nothing better than trying values of a in the increasing order from 1 up to 7 until we may be lucky enough to find a number whose sum of digits equals 10. For a equals 1, we get p equals 568. The sum of digits is 19, which is certainly not what we need. A equals 2, p is 1072. The sum of digits is 10, and the game is over. The answer is 1072, and even though this isn't required, let's write also the octal representation of the answer, given that it is really simple. Indeed, since a equals 2, c equals 8 minus 2, which is 6. Then, using the formula for the octal representation of p, we can write the answer as 2060 octal. As the last remark, 504 is actually 63 times 8. Therefore, we can write that p minus 1 equals 63 times 8a plus 1. This shows that p minus 1 is divisible not only by 9, but also by 7. And number 7 really appeared quite often in the computation. This can be explained by the fact that the last digit in any numeric system has the property similar to the property of digit 9 in decimal system. The remainder of a number divided by the last digit is equal to the remainder of the sum of its digits divided by the last digit. If you are interested in the proof, just write a comment. But I am not going to prove this here, as it seems to be off topic. 7 is the last digit in octal system. Therefore, the remainder by 7 of the number we are looking for should match the remainder of its sum of octal digits, which is 8. 8 divided by 7 gives remainder 1, which means that subtracting 1 should give the number divisible by both 9 and 7, which implies divisibility by 63. This suggests the solution used by the authors of the problem. Test any number giving remainder 1 when divided by 63 and stop once the number has sum of decimal digits equal to 10 and sum of octal digits equal to 8. I also started with this approach, however it appeared long and boring to me. Hopefully the solution presented here is less boring. And this is finally the end.